I'd like to continue our review of hypothesis testing. We're going to continue testing for the mean, but this time sigma is unknown. So you might recall that we need to use something called the t-test. Here's the hypothesis test. Here's the steps for the test. What do we have? First, verify that sigma is not known, and that will usually just be told in the problem anyways. Verify that the sample is random, and one or both of these are fine, and either, let's just say A, the population is normally distributed, or, so either one of these is fine, the sample size is greater than or equal to 30. So we need one of those to be true for all of these problems. Most of those will be assumptions in the problems themselves, so you won't have to worry about that. Later on, when we start mixing things together, that will become important. So state H sub 0 and H sub A. So you'll find the steps are exactly the same for all of these things. It just, the table that you use will be different. In this case, you'll remember, or hopefully you'll recall, that we're going to use the t-test for these computations. So with that test, you'll need something called the degrees of freedom, and that's equal to n minus 1. Determine critical values. Of course, those are for the rejection regions. The test statistic is a little bit different here. So for the test statistic, we have t is equal to x bar minus mu divided by s over the square root of n. And s is the sample standard deviation. Since the standard deviation is not known, we'll use the s that we find in the sample. And then finally, as always, make the decision. This will be a lot like the last things that you did, the last section or the last video that we did, because the shape of the t-table or the t-curve is very much like the normal distribution. So let's do some examples and see how it works. And as usual, I'll do examples both ways using the classical method or the rejection regions, and then I'll do one with p-values. So let's see what the claim is. So we have a claim is that mu is less than or equal to 6. And here's what my sample gave me. We have n is equal to 34, so that's good. N is greater than or equal to 30 is what we need, so I don't have to worry about checking anything else out as far as normality is concerned. We may use the t-table. And then from this sample, we also got a sample mean of 10.3 and a sample standard deviation of 8. Test the claim at alpha equals 0.01. So as before, I'll start with the classical method, the one that involves rejection regions. and then I'll do the p-value method to show you we get the same answer both ways. So start with the t-table, and we're going to use the degrees of freedom will be 34 minus 1, that's n minus 1, with alpha equals 0.01. Now, the thing itself, h naught is mu is less than or equal to 6, but HA is mu is greater than 6. That makes this a right-tailed test. So the rejection region will be off to the right. What we need to do then is find the table, the t-table. It's in the back of your textbook. I also have a bunch of them on my desktop. Ooh, is it small? Let's see if I can, I don't know if I can increase that size or not, but I think I can. Let's do that, bring it up and see. It gets blurrier though too. So my degrees of freedom is 33, so I'll go to the row that has 33, and then I'll look for one tail alpha, and I'll go to where it says 0.01. So that's the fourth column over. So 33, column 1, 2, 3, 4. So 2.445 is the beginning of the rejection region. So I have, let me go back to here. So from the table, I have a T naught equals 2.445. So this is what we have. Like I said, the curve is just like a normal curve. My picture doesn't look that great, but it doesn't have to be that great. Here's our rejection region, 2.445. And now let me grab the test statistic. So that's going to be T equals sample mean minus whatever the real mean is, divided by S over the square root of N. Let's put those numbers in. All right, my X bar then, where did you go? 10.3. The mu, the proposed mu, is less than or equal to 6. And then S was 8. And then N was 34. This turns out my T is approximately 3.134. So if we look, 3.134 is most definitely into the rejection region. So from this, we reject H sub 0. All right, so let's redo the previous example. Using p-values. And I'll just do the computational portion of it. So when you do p-values, you calculate the test statistic, which we did just at the top there. I'll remind you, x bar minus mu divided by S divided by the square root of N. And that came out to be 3.134. So what you do is you try to look at the p-value based on that. Remember, this is a right-tailed test, and the degrees of freedom was equal to 34 minus 1, which is 33. So let me have that table. So once again, I'll go to the degrees of freedom of 33. Now my T was 3.134. So if you look here, it's actually to the right of this column here. If we were to write it, it would be to the right of that. So if we go up here on one tail, this is a one tail of 0.005. That means that my p-value is less than 0.005. Let me see if I can get to it. Yeah, since it's to the right of that, it's going to have a smaller amount of area to its right. So what I know then from this, since my number is to the right, I know that my p-value is less than 0.005. So let me go ahead and put that in. So my P is less than 0.005. But if you look, alpha was given to be 0.01. So P is less than alpha, which implies that we reject H naught. Now, I haven't mentioned it, but in all of these problems, the underlying assumption is that the population is normal. So you don't have to check the things that I said you had to check in these problems. That doesn't mean you won't ever have to, but in the problems I'm doing, normality is already considered a given. So anyways, let's do a claim. So in this case, my claim is that mu is greater than or equal to 30. And here's my sample. N equals 18. X bar equals 28.5. And S equals 1.7. Now notice that N is not greater than or equal to 34. So we need to know that the population is normal, since we don't have a large enough sample size to ignore that portion of it. So we are given that. So I'm going to check that as that's a given in this style of problem. Now let's test the claim at alpha equals 0.01. So as before, I'll start with the classical method. And let's see what that does for us. First, let us see from the table, we're going to use the degrees of freedom will be 18 minus 1, which is 17. Alpha equals 0.01. And this will end up being a left-tailed test, because when I write these things down, I have mu is greater than or equal to 30. That's the claim. However, H sub A says that mu is less than 30. So this makes a left-tailed test. Okay. So now that we have those things, let's go ahead and look at the table. I'm going to go to row 7, the degrees of freedom 17, alpha equals 1 on the one-tailed alpha. So let's take a look. 17, one-tailed 0.001 is the fourth column. So let me take a look there. I get, it looks to me like 2.567. That's one tail. So we have 2.567. T naught equals 2.567. Our test stat that's T equals X bar minus mu divided by S over the square root of N. X bar, what was my sample? That was 28.5. And we're testing it against mu is greater than or equal to 30. S in this problem was 1.7. And divided by the square root of 18. This I get negative 3.744. And if you can't tell right now, oh, by the way, I made a mistake on my T naught, didn't I? Since it's a left-tail test, I need a negative in front of that thing. So when I look at this, my rejection region starts at negative 2.567. And then this guy right here, as you can see, is firmly inside of that rejection region. So we reject H sub 0. Let's redo the last example using p-values. So as before, all you do here is you evaluate t, so that's x bar minus mu all over s divided by the square root of n. X bar, we already did this in the last problem, so let me go ahead and put that. Negative 3.744. That's not exact, that's approximate. Let me make my approximate symbol look a little better. And now we find the area to the left of that thing. So here's what we have. I'll just so you can see. You have to make everything work on the left here. Negative 3.744. And the p-value will be that area in that little piece. So let's take a look from our table. We have the degrees of freedom will be 17. And let's go ahead and take a look. So if I go to the 17 table, now remember, I need to pretend that I'm working with a positive t value. So I'm actually going to try to find 3.744 in the table. Let's go and take a look if it's even there. I don't think it will be. But in 17, 3.744, you can see that it's beyond this last column. And once again, that means that the p-value is less than 0.005. So you'll get the p is less than 0.005. But we know that alpha equals 0.01. That implies that p is less than alpha, and so that tells us to reject H naught. And now let me do an example that involves an equality so that we have a two-tailed test. So the claim on this one, the claim is that mu equals 11.5. And the sample, we have n equals 34. So once again, that's a good n to have. X bar equals 12.2 and s equals 2.2. Let's test the claim at alpha equals 0.10. This will be the classical method. So first, let me get these down. Many times I forget this, but you shouldn't. Mu equals 11.5. That is the claim. And that means the alternative hypothesis is that mu does not equal 11.5. And this makes it a two-tailed test. So you know what that means. I'm going to have to divide my alpha into 2. Alpha divided by 2 equals 0.05. Whenever I use the table now, I'm going to have to use an alpha equals 0.05, but make sure that I use the two-tailed version. You'll see when I get there. Let's go ahead and see what that's talking about. Our degrees of freedom, in this case, df, is 34 minus 1, and that's 33. So alpha is 0.05, df is 33, and we're ready to get our t naught. Remember, you're going to get a positive and a negative because it's a two-tailed test. So let's go ahead. I'm looking at the 33 row, but the 0.05 column. So the 33 row is here. Now I need two tails. See it? Degrees of freedom, two tails, 0.05. So it's the third column, and then I need to go to row 33. So I get 2.035. So make sure you can see that. 33, 2.035, two tails alpha. As a picture, I'll go ahead and draw it before I do the T statistic. Here's what we have. We have 2.035 here, negative 2.035 here. And now let's go ahead and calculate our test statistic. Here, t, that's x bar minus mu divided by s over the square root of n. What do we have for there? X bar in the sample was 12.2. The mean that we're testing is 11.5. So this is going to take place in the right tail. We can see that. S will be 2.2 and N will be 34. I get about 1.855. So if I look here, it is right around there. So we see that we fail to reject H naught. And then to finish it off, let's go ahead and do a p-value computation. So let's redo the last example with p-values. So let's see what happens there. We already did the t statistic. So our test stat, that's t equals x bar minus mu s over the square root of n. And we already see that that's about 1.855. And the degrees of freedom was 34 minus 1. That's equal to 33. So let me look in the row 33 row and try to find this number if possible. So let's take a look. The 33 row is down here, and we are 1.855. 33. Do you see this here? Here, it's between 1.692 and 2.035. So if I look at the alphas up here, it's strictly between 0.05 and 0.1. So I know that 0.05 is less than, now p, the p-value is twice the area on the end because it's a two-tailed test. You have two pieces. So each of these is only 1/2 of a p, and that is less than 0.1. So that's what I found between those two values. If I multiply through by 2, I get this. Now, what was my alpha? My alpha here is 0.1. So this tells me that alpha is less than p, which implies that we fail to reject H naught.